Welcome everyone. In this video, we're going to talk about improper integrals. So improper integrals are when you have infinity as your limit of integration, either the limit of integration on top or on the bottom. As you can see here in this example, we have infinity right here. So this is an improper integral. Another type of improper integral is when your function in the integrand, it has a vertical asymptote. So one of the limit of integration happens to be a vertical asymptote. So the way you're going to treat them is like a limit problem. So we're pretty much going to take the limit of some variable goes to infinity and see what it happens to the function. So I'm going to go ahead and replace that improper component with a limit. So I'm going to say, okay, let's take limit as maybe some b goes to this improper value, infinity, of this integral from 0 to b, because I'm replacing b with infinity, of the same function, 1 over 1 plus x squared dx. And then you just carry out the integration. So you finish this up from your knowledge of integration, and at the end, you take the limit as b goes to infinity of the result. Now, this integral, you should know this is the tangent inverse or arctangent. So we have the limit as b approaches infinity of tangent inverse of x. We're going to take it from 0 to some b. So let's plug in the upper limit of integration, and then we subtract the lower limit of integration. So we have the limit as b approaches infinity of tangent inverse of b, since that's my upper limit of integration. I replace it in x minus tangent inverse of 0. So we're using the fundamental theorem of calculus. Now, this piece right here, tangent inverse of 0, well, we know that's 0. So that will go away. So we're taking the limit as b approaches infinity of tangent inverse of b minus 0. And you can ignore the 0. So I'm going to get rid of that. Now, what happens as b grows? So what happens to tangent inverse as b approaches infinity? Here, you might need to know the graph of tangent inverse, so you're familiar with how the behavior of the graph goes when it approaches infinity. So tangent inverse has two asymptotes, one here at pi over 2 and at negative pi over 2. When the graph passes through 0, because tangent inverse of 0 is 0, and it's going to create this shape getting closer to its asymptote right here. And right here, it's going to get closer to the other asymptote. So these are the two horizontal asymptotes for tangent inverse. So as b grows, so let's say b is keep going to infinity, the graph looks like approaches its horizontal asymptote. So this limit is simply pi over 2. So since we got a value, not infinity, we're going to conclude that this integral is convergent. Convergent is just another vocabulary we often use to indicate that the function reaches an actual value rather infinity. Now let's take a look at this problem. So I don't seem to have infinity anywhere in my limit of integration, but I do have a value which makes this integrand undefined. So if you plug in 0, it's fine. You get 1 over 4 minus square root of 4 minus 0. So that's a real number. But if you plug in 4 into x, you'll get undefined statement. So that means it is improper at 4. So we're going to treat it as approaching 4 as a limit problem. So we're looking at the interval, let's draw it, from 0 to 4. And it is improper here. So it's improper here. Now, which direction are you approaching? So here's coming from the left, here's coming from the right. We're not coming from the right because we're not looking at greater than 4. We're looking from 0 to 4. So we're going to approach the limit, we're going to use limit approaching 4 from the left. So let's take a look at limit as, let's say, some variable t approaches 4 from the left of the integral from 0 to some t of 1 over square root of 4 minus x dx. So that's where I'm going to rewrite the limit. So every time you have a real number, the function has a vertical asymptote or undefined, you can approach the limit approaching that number either from the left or from the right. Here we were approaching from the left. So let's go ahead and carry along with this integration, and then we'll take the limit approaching 4 from the left. So I'm going to rewrite the function this way. I will bring the square root on top. So you'll have 4 minus x to the power negative 1/2 dx. So it's the same thing as writing it in the denominator. So use a u substitution. So let u be equal to 1 minus 4 minus x. Then your du, it's going to be negative 1 dx. So I don't have a negative in the integrand, I can pull it out. So my integral looks like 0 to t of the negative u to the power negative 1/2 du. And we're taking the limit as some t approaches 4 from the left. So that's what this looks like. So now using the power rule of integration, we integrate, we add 1 to the power, same power goes on the bottom. So we have the limit, keep writing, t approaches 4 from the left of negative u to the positive 1/2 over 1/2, which is same as multiplying by 2. And we're going to take it from 0 to t. Now, using the fundamental theorem of calculus, we plug in the upper limit of integration and then minus the lower limit of integration. So we have the limit as t approaches 4 from the left of negative 2 times. Now I need to plug in what u is before I substitute anything. So I'm going to go ahead and substitute u in here so that I don't misplace my function. So u is right here because the limit of integration limits belongs to x. So this would be 4 minus x to the power 1/2. Now I can take it from 0 to t. So I needed to substitute that before I plug in for u. And now I can plug in t for x. So you'll have negative 2 times 4 minus t to the power 1/2 minus 2 times 4 minus 0 to the power 1/2. All right, so now let's clear this up before we take the limit. So we have the limit as t approaches 4 from the left of, now I'm going to go ahead and rewrite the power 1/2 as a square root. So these can be written like this so that it's easy to look at. Since we finish integrating, we don't need to write power 1/2. I can write it as a square root. So I have negative 2 square root of 4 minus t plus 2 times square root of 4. And that will simplify. So now I can take the limit. Now, since this is not an undefined expression, I can plug in 4 because I'm taking the limit as t approaches 4 from the left. You can ignore the direction and substitute 4 in there. So you have negative 2 times the square root of 4 minus 4 plus, and then the limit of a constant is just the constant itself. So that will just be 2 times 2. And this will give you negative 2 times 0 plus 4, which would just be 4. So this integral actually converges, and it converges to this value. So this is also a convergent integral. All right, so for this problem, we see that it is also improper, and it's not improper here, not in between, but up here. So it happens to be improper at 2 because when you plug in 2 in here, you get 4, and then 4 minus 4 is 0 in the denominator. So that's a problem. So we're going to approach the limit, approaching that number. Now let's pick our direction. So again, we're looking at from 0 to 2. So this is the interval. So we're coming to this direction. So that's from the left. So I will rewrite this as a limit of some b or any variable you pick. I think previously I used t, but doesn't really matter. So 2 from the left of this integral from 0 to b of 1 over the square root of 4 minus some s squared ds. Now you should recall what this integral looks like. So remember from before, we integrated something like this. If you have an integral of some a squared minus x squared, this is sine inverse of x over a plus c. So that's the sine inverse function that we know from before. So that's what it is here. A is actually 2, and then this will be sine inverse of s over 2. So this integral becomes the following. So we have the limit as b approaches 2 from the left of arc sine or sine inverse of s, because that's your x, over 2. We're going to take it from 0 to b. Now, using the fundamental theorem of calculus, plug in the upper limit and the lower limit, then we're ready to take the limit as b approaches 2 from the left. So we have sine inverse of b over 2 minus sine inverse of 0. And by now, we know sine inverse of 0 is 0, so that goes away. So we're only taking the limit of sine inverse of b over 2. So this is the limit as b approaches 2 from the left of sine inverse of b over 2. Now, as b approaches 2 from the left, I can go ahead and do the direct substitution since I don't get an undefined statement. So this is the limit. Well, I'm making direct substitution, so I can drop the limit. We're evaluating sine inverse of 2 over 2. So I simply replace b with 2, and we know this is equal to sine inverse of 1. And also from our knowledge from before, sine inverse of 1, we know that's pi over 2. So this answer is pi over 2, which means this integral that we've been working with, this is going to converge to pi over 2. So that's the value for this integral. So here we have another interesting improper integral. Now, we see infinity, we know it's improper over there. But if you look at it carefully, you're looking at this interval from 0 to keep on going, right? Infinity. But then this denominator happens to be 0 in between 0 to infinity. So when x equals, or theta equals 1 in this case, it's also going to be improper. So we have to break it up into two pieces. So it's improper at 1 and of course infinity. So we're going to break it up from 0 to 1 of 1 over theta squared minus 1 d theta. It's improper at 1 plus then 1 to infinity of 1 over theta squared minus 1 d theta. Now you only work on one integral, not both of them, hoping that it's probably going to be infinity. If it's convergent, then you actually have to work out both. Now I'm going to go ahead and working on this integral. Let's hope it's going to diverge, but we need to make sure it does so that we don't need to work out the other half of the problem. So it is improper at 1, so I'm going to go ahead and take the limit as some t approaches 1 from the left because you're looking at the interval 0 to 1. And I'm going to factor the denominator into the following. So we have 0 to t of 1 over theta plus 1 and then theta minus 1 d theta. So this is a partial fraction problem. So you can break it up into the following. So we have the limit as t approaches 1 from the left of the integral from 0 to t of some a over theta plus 1 plus b over theta minus 1. So if you need help with how to set up partial fractions, I have a separate video. You can check it out in the description box. So that's how we're going to treat this integral right here. And once we have our final answer after completing partial fraction and integration, we can figure out if the integral converges or diverges. So carry on with this, solve for your constants a and b. So I'm going to go ahead and try to solve for these. So put them in common denominators, multiply both sides of this integral by LCD. So you'll have 1 is equal to a times theta minus 1 plus b times theta plus 1. So I'm taking this integral and setting it equal to this integral and solving for the unknown constants a and b. So pick a value for theta, solve for a and b. So if I choose theta to be 1, then this goes to 0. So you'll have 1 is equal to b of 2. So that would be b times 2. That would be b is equal to 1/2. So b is 1/2. And then pick theta is equal to -1. So this will disappear. So you can solve for a. So you will have 1 equals a times -1 minus 1, that's -2. So this would give you a equals -1/2. All right, so I'm able to solve for my a and b very quickly. Now I can finish up the integration. So that's what I'm going to replace right here. So I got a is equal to -1/2 and b is equal to positive 1/2. All right, so now integration is pretty straightforward because these are both going to turn out to be ln. So carrying it up here, we have the limit as t approaches 1 from the left of negative 1/2 ln of theta plus 1, and then plus 1/2, the second integral will be ln of theta minus 1. And we're going to take both of these from 0 to t. So that's our final statement. That's what we're going to do. Plug in the upper limit and then the lower limit. So we have the limit as t approaches 1 from the left of negative 1/2 ln of t plus 1, and then plug in 0. So minus 1/2, that's plus 1/2 ln of 1. So this is going to go to 0. For the second half, we do the same thing, plug in t first. So we have 1/2 ln of t minus 1. And then we plug in the lower limit of integration. So we have minus 1/2 ln of 0 minus 1. When you start to see that, it's also 0 because that's also ln of 1. So the only thing that we're going to have to take the limit of is this and this right here. I'm going to go ahead and combine them by using laws of logarithms. So we have the limit as t approaches 1 from the left, ln of t minus 1 over t plus 1 in absolute value. If you try to substitute 1 in there or 1 from the left, you'll see that your input right here is going to be 0. And we know ln of 0, well, we can define ln at 0. If you look at the graph, it'll look like this. So we're approaching negative infinity. So this limit happens to be negative infinity, which means that we don't need to do the other half. We can say that since the integral from 0 to 1 of 1 over theta squared minus 1 d theta diverges, this implies that the integral from 1 to infinity of 1 over theta squared minus 1 d theta also diverges. So that's the conclusion we can draw from this integral. So I hope this makes sense. These problems are could be tedious sometimes, but just carry out the integration with the techniques you have learned, and at the end, take the limit and see what happens.